This is a lesson on periodicity or periodic trends. There are general trends or patterns that follow. Not everything follows exactly correctly, but it's good overall. It's correct more times than not. The first of these periodic trends is the atomic radius. Atomic radius is another word for how big is your atom. It's from the nucleus to the outer edge of the electron cloud. The atomic radius has bigger atoms at the bottom left corner of the periodic table. So here's your periodic table. This is where the big atoms are. Then the opposite corner will be where the small atoms are. If I give you two atoms within the periodic table, the one closest to the top right-hand corner is the smallest. The one closest to the bottom left-hand corner will be the biggest atom. There are two trends within this overall diagonal trend going down. As you go down a group, the atomic radius increases. And the reason for this is there are more layers. At the top of the periodic table, you only have one layer of electron clouds. If you have at the second period, you have two layers. So on, and so on, and so on. Don't say there's more electrons. Say there are more electron layers. It's like up here you're wearing a t-shirt, here you're wearing a t-shirt and a shirt, then you're wearing a t-shirt, a shirt, and a vest, a t-shirt, shirt, vest, and a sports coat, a t-shirt, shirt, vest, sports coat, overalls, overcoat. When you get down here, you're like that little kid on the Christmas Story where you can't move, you just stuffed up, can't move, arms down. This is fairly obvious. If you have more layers, you're going to have a bigger atom. What is less obvious is as you go from left to right, the atomic radius decreases. What happens is you have a greater proton density. In the fourth period, you have at one end krypton. First of all, it's the fourth energy level that's going in. So you have level 4 at the left-hand side and level 4 energy level on the right-hand side. Then over here with krypton, you're going to have potassium. You have 19 protons. Over here you have 36 protons. Within the same volume of space, you have almost twice the number of protons. That density pulls in the electron clouds a tiny bit. It's nowhere near as dramatic as the layers, but there is an effect so that the size decreases as you go from left to right. So atomic radius is a trend where the biggest atoms are in the bottom left-hand corner, where the smaller atoms are in the top right-hand the next two patterns derive directly from the size. Ionization energy. The ionization energy is the energy needed to rip out the electron from the atom. It's the energy needed to remove the least strongly held electron. Usually the least strongly held electron is on the outside. On the outside, electron is farther away. This electron out here is farther away than the inner cell electrons. Plus, you have other electrons in between. It's called electronic shielding. This negative cloud here disperses the power on that electron out here. So A is farther away, and B is being blocked by all the other electrons. So ionization energy is the energy needed to remove the least strongly held electron. The closer to the nucleus, the more energy is required. Farther away, less energy is required. So closer to the nucleus, more energy is needed. To remove that electron. If it's really close, it takes more energy. The negative and positive have a really strong connection. If it's farther away, it's less strongly held. Analogy to that would be there's a hill with a car. You want to push the car up to the top of the hill, and if you're at the bottom of the hill, it takes more energy. So if you're close to the nucleus, you're at the bottom of the hill, it takes more energy to push it up to the top. If you are halfway up or more than halfway up the hill, it does not take as much energy to push it up over because you're closer to the edge. So if you're out here, it's only this much energy to remove it. If you're here, it's this much energy to remove it. So it's like being at the top of the hill, or close to the top of the hill, it's easier to remove it. Another factor on ionization energy is the more electrons you remove, the vastly more difficult it is to remove electrons. It takes more energy. So the second ionization energy requires more energy than the first ionization energy, or the energy to remove it. The first, much more energy. Than the first. Ionization energy, first electron. When you take the first electron away, you're taking the negative electron away from a positive cation. Now it's a +1 cation. +1 cations don't want to lose negative electrons, it wants to take a -1 electron. So it's doing the opposite. It's forcing it to do something it doesn't want to do. It's homework. Forcing it to do something you don't want to do. The third is even more, fourth and fifth is higher yet. It increases much more with each additional electron removed. Another complication on ionization energy is the idea of a stable octet, which we'll talk about more later. A stable octet is when you have a noble gas configuration. If you have 8 electrons, that's where the octet comes from, in our shell. This is energetically most stable, it's symmetrical, so what happens is it really doesn't want to add or remove any electrons. Electron affinity is sort of the opposite of ionization energy. Ionization energy is the energy to remove the electron. Electron affinity is the energy released when an electron is added. This is kind of like the opposite of the heel. If you let the brakes go, you would get more energy out if you're going to the bottom. If you're here, if you're at the top of the hill, you're going to get more energy out of it. If you let the brakes go, it slides down. So that means it's going closer to the nucleus. So that means it's a small atom. If you are, if there's a ledge, if the cliff is not as high, this is a large atom, then you're not going to get so much energy out of it. Small atoms welcome the electron. Put these together, and both ionization energy and electron affinity have the same pattern as each other, but opposite of the size of the atom. Here's the small atoms up here, but you have big ionization energy and big electron affinity. That means here is the opposite. Small ionization energy and small electron affinity. Down here, francium, you sneeze on it, it'll lose the electron. It does not take much energy to remove the electron. Up here is you get a lot of energy out when you add an electron to fluorine and you make it negative. Now, affinity and ionization energy, the noble gases, we kind of tend to ignore because they don't react very much. And the last thing we're going to talk about is the ionic radius. The ionic radius means that if you have a positive ion or cation, you have the more protons than electrons, so the protons outnumber the electrons. Protons will pull it in, and if the cloud is pulled in, cloud shrinks so that the size of the ion is smaller than the size of the neutral atom. That's if it's positive. It's lost electrons, you're losing electrons, and the positive charges outnumber the negative electrons, so it sucks it in. Anion is the opposite. Anions are negative because you have added negative electrons, so the electrons outnumber the protons. There's less stuff holding the electron cloud in, so the cloud expands, which means the ion is greater than the atom. The analogy I use, for this, if you have two positive parent protons taking care of one negative electron kid at Walmart or someplace, the two parents keep the kid in tow, so his roaming range is very small. Now, if you have a negative anion at Walmart, that means you have, let's say, only one parent, you have 3 or 4 kids, that one parent can't control all those kids, so their roaming radius expands. So here, proton parents outnumber the electron kids, a very small range. Here, the negative electron kids outnumber the positive proton parent, and the cloud expands. Kids are all over the place. That concludes this lesson on periodicity.